Yeah, get your clickers ready. We're heading for exam 3. And exam 3, 2 Tuesdays from today. Man, it's almost Thanksgiving. 2 Tuesdays from today will be the Tuesday before Thanksgiving. Man. It is going to be the test which, if you crush it, will ditch your lowest of exam 1 and exam 2, whichever one is lower. So you really want to start to prepare yourself mentally to crush like a bug exam 3. And I don't mind. If everybody in here takes me to the cleaners on exam 3, great. That's what I want. All right? So, and I don't care what your stinkiest grade is right now on the books. Now, I'm not looking at anybody, but, there's a few grades that are, but no matter where you are right now, if you prepare, you can crush exam 3, and that's what I want. All right. And exam 3, though, you're going to have to really think. Nothing that we do in exam 3 is bodaciously difficult calculation-wise, but concepts-wise, you're going to have to keep a lot of things organized in your mind. You have to be really light on your feet and agile, mentally agile as you go through exam 3. Now, as for homework, I set up homework 18 a little bit late yesterday, and so I decided to make it due on Tuesday next week, so I'll give you guys a little break on account of me being a little bit pokey getting it out. Now, it's not a big, huge assignment. If you've already got it done, so much the better. But if you, what's that? For Thursday? No, it's set for Tuesday. Okay? And then we're going to have another. I sympathize with Sedora. I understand why you're asking me that. But similarly, homework 19. Now, that's going to be a new one based on today's lecture. And it's going to be going up. I'll probably try to activate that tonight or maybe first thing in the morning. So be ready for that. So you're going to have 2 homeworks running this weekend. And by the way, if you have a study partner that you don't meet until Tuesday, then one of the things that you can do is make a virtual study partner or a virtual study group out of discussions. And every semester is different. Some semesters, the study group, the discussion area is like a beehive. And other sections, it's like a ghost town. Right now, this semester we're doing all right, but if you really want to get down to business, post some threads and discuss, talk things over. And I know there's a lot of students in here that have helped other students in that way, and that's good. So we got a ton of homework. Also, homework 19, I'm going to put another thermal equilibrium problem on there, maybe 2, so you have a little bit extra practice. I talked to some students yesterday in office hours, and they were saying, Dr. B, how about I wouldn't mind an extra shot at thermal equilibrium calculations. All right, now I'm not looking at anybody, but it's one of your classmates that I talked to about that. So I'm going to put 1 or 2 on there so you have a good shot at a little extra practice. So now it won't be coffee and cream again. It might be, something else, but Oh, I have one that I haven't used for a while. No. I'll come up with something good. But it won't be coffee and cream. It might be, ice cream and... No, because that'll melt. Well, I'll figure something good. Coffee and cream. Some variation on that. All right. So, and also, I'll just remind you now that there's 2 talking PDFs about the thermal energy calculation. And in discussions, a few of the students, they went and dug around in YouTube or whatnot, and they found this big, monstrous formula to use to figure out in one fell swoop the equilibrium temperature without doing the table. And yeah, that's nice, but what if I give you a variant on exam 3 and you don't know how to use the table and you can't use the formula? So then what do? All right? And so that's the challenge to you guys. The reason I don't give you guys that big mega formula that you see in discussions is because I want you to think about the physical process, not some, you can get any number of engineering students to memorize formulas and stuff. That's what they like to do over there. But that's not what you guys want to do. You guys want to be their superiors. And, the engineering students, they all have bosses, right? What if you should be the boss of a bunch of engineers? Why not? You got to keep them in line. You got to be smart. You got to be able to think on your feet. And that's what I want you guys to do. Now, enough. Well, let me pause for questions. Yes. Well, we have a chapter coming up on next week on electricity and magnetism, and that's not in the website yet, and it won't be. So thank you for reminding me. I didn't say it to the morning class, but I'm gonna give you guys that chapter for free. Okay, I'll make it into a PDF or something, and I'll put it so it won't be all fancy up like the website, and you won't have I'll make all the reviews for that in web courses. So, and the same with chapter 9. That'll be our last chapter of the semester. So, what I was saying about the talking PDFs of thermal equilibrium, I posted talking PDF for both sections, and if you want extra practice or extra study, you guys should look at the one that I did for the 9 a.m. section. We did it slightly differently than how we did it in this class. So that's a good thing to do, a good study tool. All right, last time we discussed wave concepts, including phase. Phase meaning the relative position of a part of your wave relative to some starting point. So I said, well, if you consider the peak to be 0, then the trough you can assign the number pi, 3.14159, blah, 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 to that trough. And then the next peak, 2 pi, and so on. And you can do it in degrees as well. You can do the peak being 0, the trough 180 degrees, and then the next peak 360 degrees, and then you start over, just like a circle. Now, what you're looking at here is not a circle. It's a wave, and it has a propagation speed v to the right. But many of the factors that we use to study circles are useful for studying or for identifying parts of waves, and one of those is the phase. And so what we're going to do is elaborate on the idea of phase with 2 waves, and then we're going to do some clicker questions. So let's just go back and take a look at some of the basics. Okay, get your clicker ready. And Matter of fact, let's start with the clicker question right now. It's not about phase, it's about amplitude. All right, so hopefully you'll be able to answer this one in a righteous manner. Question number 1 for today. What's the amplitude of this wave? Look at it carefully. Hit your refresh key. And hopefully this is cinchy for you guys. Good. I see you guys pointing with pencils and fingertips at the diagrams and stuff and talking it over. Good. My wonderful students, amplitude is a very basic concept. So you want to be able to identify, look at a graph like this and tell me the amplitude is something. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, good. Most of you guys got this right. Yeah, the amplitude is 50. And just to reinforce, the amplitude is the distance or the magnitude of whatever you're measuring from equilibrium up to the peak, or from equilibrium down to the trough, or half of what you measure from peak to trough. I mean, you can think of it that way. Go peak to trough, divide by 2. That's the amplitude. All right? Now, the amplitude, you can make a side note to yourself. The amplitude might not be distance. Now, if you're looking at a wave in the ocean, you can think of this as a wave. The amplitude here, 50 feet. Oh, my goodness. That would be it. Actually, the wave height would be 100 feet. And I think surfers get, in certain parts of the world, they can get, the conditions are right, they can get waves up, in that neighborhood of 100 feet. Like over in Portugal, there's a certain place where they could do that. But it might be, if it's an electromagnetic wave, it might be the size of the electric field that goes up and then goes down relative to some equilibrium value. All right? Now, for a water wave, the equilibrium value, the 0 point or the 0 line, is sea level. If it were a sound wave, if this represented a sound wave, you would have some variation in the air pressure. That's what a sound wave is. It's a sound wave. It's a little tiny variation, a wave variation in the air pressure. The air pressure gets a little bit higher, then a little bit lower, then a little bit higher, then a little bit lower at a very particular rate. If you're singing or if you're playing a musical instrument, if you're hitting a high note, but if you're speaking, you're putting out a lot of different frequencies, a lot of different pitches. But as soon as I go like this, la, see, I got your attention on that. As soon as I do that, hit a fairly good note, then most of the sound waves, at least for me, are at that frequency. And the amplitude is a little bit of extra pressure produced by my vocal cords, followed by getting back to the ambient air pressure. So whatever the air pressure is right now, like 1,001 millibars or something, whatever it is today, right now in this room, Your sound waves are variations above and below that. So it might go up to 1,002 millibars and then down to 1,000 millibars, then back up to 1,001 equilibrium and then up to 1,002. Then back down to 1,001 equilibrium and then down to 1,000, your lowest air pressure. And so that's how sound waves work. And they propagate at the speed of sound. And just like this. So this vertical scale, it could be a distance measurement, it could be electrical or magnetic field measurement, it could be a pressure measurement, always relative to equilibrium. Now, another thing that we talked about last time was the idea of phase. The customary but not universal symbol is Greek lowercase phi, P-H-I. And so if you say, all right, I'm going to start my phase counting system, it's basically a counting system. At the top of this first peak, phi equals 0. Then the next peak is going to be phi equals 2 pi. That's one full wave away relative to the first. And the reason that we use 2 pi or fractions of 2 pi is because the full length of the circumference of a circle is 2 pi times whatever the radius is. Okay? But half of a circle, halfway around, is pi times. So, here's another peak, 4 pi, and then down here, here's half a cycle, your trough. If you start up here at 0, get my cursor. If you start up here at 0, then this trough right after that is pi. All right, and you can name all the other parts of the wave in that manner. For instance, this one out here, this trough would be. What would the value of this trough be? It'd be 3 pi. Okay? Now, I'm going to ask you another clicker question. Here we go. Just what is the phase at this equilibrium point? Okay, here it is, this black arrow. Here it comes. All right? So that's the first crossing point of equilibrium after phi equals 0. So what's the value for phi there? I mean, logically, what would it be? It's good. Definitely talk to your, kind of work it out. See, I see everybody pointing in. I love seeing that. 30 seconds. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good, 190 of yous. This is. So here's your setup, right? And so halfway between 0 and pi. That's it. Pi over 2. So if you voted, I think it was B on that one. You got that one right. All right. Now, final note on, well, it won't be the final note, but it's a side note, is that you can start your phase accounting anywhere you want. I started this one at the top of the first wave, at the crest. But you could have started it, at an equilibrium point at sea level. Or you could have started it in a trough. It depends on what you want, what you're set up for, what kind of things you're measuring. what kind of, how you are set up for measuring. So now we're going to keep talking about phase here, but before we do that, I want to go through a couple other things about waves. Last time I mentioned that they're not easily localized. And, they transport energy and momentum across space-time, but they're not easily localized. And they behave way differently than a Newtonian particle like a baseball. Now, what we're going to do here in a minute is see how two waves interact. Now, if you have two Newtonian particles, here's a good example of two Newtonian particles that probably many of you have seen, and that is billiard balls. If you've ever played a game of pool, you know that the cue ball, collides with, one of the other balls, and hopefully you get it right, and it goes into one of the pockets, and you get some points. And waves don't do that. They interact with other waves, but not like billiard balls do. All right. One of the ways that they do that is by diffraction. And diffraction is pictured in this particular diagram. This is a shadowgram, shadow graph, I guess maybe you should say. It's a photograph of a shadow. It's made with a tank of water with a glass bottom, filled with a fairly shallow amount of water. So you could shine a light above the tank, through the water, through the glass bottom, and down onto the table. And if you have a piece of white paper on the table, you can then take a photograph of the image that you see. And that's what this image is. It's an image of waves in a wave tank that are going through a gap in a barrier. And in that barrier, in that gap, wavelets form. It's as if there's little tiny sources of waves. When you throw a pebble into a pond, it'll make rings go outward. And that's what this gap is like. It's like a zillion little pebbles being dropped in, but the source is not some little guy with pebbles. It's these waves. These waves coming through from bottom to top, they come in like waves down at the beach. The waves down at the beach, they all seem to be fairly parallel when they come in. And then they break and stuff like that. But if they were to go through a gap in the jetty, this is what they would do. You would get a central, see here are the waves, they start to curve. These are no longer flat the way they are down here. They're coming in flat, they come out curved. And also, they get curved off into different directions. Now, over here on the left, you can see some waves over here. And over on the right, you can see some waves over here. That is diffraction. Baseballs do not do that. Billiard balls, in the kinetic theory of gas, we don't think that molecules do that. Although in the quantum theory of gas, yes, particles do diffract. But in the old-fashioned, Joule, Kelvin era, when they were thinking about molecules, they were thinking about billiard balls. And the ideal gas model thought of them as just ricocheting around and not ever doing anything like this. Another thing that wavelets. Another thing that waves have is the more energy you add, you don't change the speed of propagation normally. All right? Now, exceptions to this might be, some really complex fluid like the surface of the sun, where you have these, extremely high temperatures, extremely strong magnetic fields in the surface, sunspots. They're related to the magnetic fields, really intense. And all those prominences and stuff ejecting and looping off the surface, that's all magnetic fields. Very difficult to study. It's one of the harder parts of physics. But normally speaking, adding energy to a wave does not change the speed. Speed is a constant. So the speed of sound, if you Oh, I got a microphone here. Let me turn off my mic. I'm whispering into a microphone, ain't whispering. All right. If I whisper like this. Can you hear me, Daniel? If I whisper like this. Or if I whisper like this with a lot more energy, the sound doesn't get there any faster. But now try that with a baseball. Load up a baseball with energy, and it's blazing. You're talking Brett Favre versus, some little shrimpy first grader throwing a football. All right? You're talking heat versus, not so. But for waves, and guess what? Here's the weird thing. You know what does change? In the theory of relativity anyways, you know what changes? The color. If it's electromagnetic radiation, what changes is the color. So if you have this is a little sneak preview of relativity. If you have somebody in a spaceship coming at you at half the speed of light, and you shine a flashlight or a laser at them, you're standing here on Earth, and you shine a laser, and they're coming at you at half the speed. Does the light come at them at 1.5 times the speed of light? Because that's what it would do here on Earth. If I'm going 60 down the highway and somebody's coming 60 towards me, then we're closing at 120 miles per hour. All right, that's what makes head-on collisions so dangerous. But with light, it's not like that. You know what changes? You don't have more energy, you don't have more speed, but what changes is the color of the light, the color of the photons. Oh boy, it's very, very interesting. And none of that happens to baseballs. Now, so the simple wave equation, you have equals lambda f. We're going to deal with that today too. All right, now, I want to show you some waves interacting. I spent some time this morning making some brand new images. And try to make a sketch of this. This is the blue one. Here's a blue wave, kind of motate. And, its amplitude is 50. And I didn't make it. This is actually an electromagnetic wave. I use the speed of light for doing this on my computer. But I mapped it out so it shows, a few squiggles. All right, so this is a few wiggles in the strength of the electric field. All right, so the amplitude is 50, and it looks like for the blue one, it looks like the trough, the first trough that you get to is fairly close to halfway between 0.03 and 0.06. But then this trough over here, the next trough, it's definitely further. It's not at the halfway point. And this peak looks halfway from 0 to 0.03. All right? So try to make these, and these are all very precise. Okay? Get a location on your peak and your trough, at least these two, in the blue wave. Now, I've got a red one, and I'm going to want you to sketch it. All right? And here's the red one. Also, amplitude 50. Now, this one, I made it shift a little bit to the right. So notice that the trough, the first peak, is no longer about halfway between 0 and 0.03. And the trough is definitely not. But now look at this. The second, see, look at this. The second trough is at about 0.12. And the third peak is right about 0.15. So try to make your sketch reflect that. All right? Now, I've got, I was working through this with the 9 a.m. section, and we were looking at these waves, and I'll just go back. Here's the blue one. If you want to double check your blue. All right, and we're going to add these two together, the red and the blue. And we're going to get purple. All right, so there's the red. And notice that so there's the blue. Here's the red. Amplitude 50. And through discussion with the 9 a.m. section, I decided that I'm going to make part of homework 19 a study of these two images and then the image that's going to come up next. Now, the image that comes up next, all these things I did on a spreadsheet on the computer. So they're very precise. All right, now your sketches might not be as nice, but if you can jot in at least two of the peak and a trough, the way I identified it, hopefully that'll help. Now, here's the red, here's the blue. Now, they're shifted relative to each other, and that's nice. So that's like sound wave. If this was sound waves, it'd be like sound waves coming in from, somebody over in the corner over here, and sound waves coming in from somebody in the back. Two slightly different locations. That happens all the time. It's normal. All right? So what we're going to do is put them together. Now, here they are on top of each other. This is not what you would hear if these were sound waves. But you can see the blue one, the first peak is about halfway from 0 to 0.3 as before. The red one, the third peak is at about 0.15 as before. All right, so try to get this sketched in. All right, so they're both amplitude 50, but but what we would say is they're out of phase just a bit. Now here's the amount that they're out of phase, delta phi. It's just that little red peak to blue peak. And that distance is going to be the same up here. Red peak to blue peak over here. And hey, red trough to blue trough down over there. In fact, when you compare, look at this. Same thing here. Equilibrium to equilibrium, red to blue. That delta phi is the same. It's like a shift to the left or to the right, depending on which way you look at it. Now, this is what they look like if you put them both, you trace them out on tracing paper and then you overlay them. But that's not what you hear. This is what you hear. Now, make a sketch of this. Notice the amp, and this is literally adding up the y coordinates for both those graphs and then replotting it as one curve. And notice that the amplitude is almost 100. Right now, the amplitude here, 50 and 50. But notice that right here, they both have the same value. That's actually where they have their peak. And you won't be able to do this with your sketches most likely, but this peak right here, and I'll show you this in homework 19. I'll get this. I'll put in some more graph paper lines so you can see it. This peak up here, higher amplitude, and it's shifted with respect to the blue peak and the red peak. Matter of fact, it's halfway between them. Because the blue and the red are equal except for a little bit of a shift. So the combination peak is going to be 50-50 right between the two, the blue peak and the red peak. All right? So if these were sound waves, this is what you would hear. All right, you think about it. Me singing into the microphone, la. I don't even know what note that is. I can't even read music. I sing in the choir, but I can't read music. Me hitting a note like that, you're getting the sound waves from at least two different speakers in here, all right? And you might be getting it from the guys up in front directly from my big mouth. So that's what we got. That's what you hear. You hear one sound. All right? And the peaks from one speaker and the peaks from the other speaker, they might not line up, but when you hear them, your brain adds them together and you get this purple signal. All right, so same amplitude. So same wavelength and frequency, but more amplitude. And the peaks are shifted. The troughs are shifted. Everything's shifted. All right? And this is an example of something that we call interference. So make a note. Big, big vocabulary word, interference. And so much of the really cool stuff. Diffraction is an interference phenomenon. A whole lot of cool optical effects. For instance, laser optic, so if you have a fiber optic cable for internet, there's a whole lot of interference effects that are designed purposefully for the benefit of that. And so that's what we're going to, so light is an electromagnetic field that oscillates. And guess what? In the 1800s, well before Einstein was born, they knew that the electromagnetic field, they figured theoretically that there were waves that could be made in the electromagnetic field. And initially nobody knew how to make them. They figured it out eventually. But they figured out theoretically that the energy was proportional to the square of the amplitude. And guess what that means? That, my friends, means oscillation. Energy proportional to the square of something. There's in the exact formula, it's the sum of E squared, the electrical field squared, plus the magnetic field squared, in parentheses, and then a bunch of stuff out in front of it, like the speed of light and a couple other constants. But it's proportional to the squares of the field amplitude. So it all works kind of cool. Now, I told you that we're going to look at this wave equation. Here we go. And you're going to be doing some calculations here in a second. So get your calculator out and be ready to notate. Now, in this wave equation, this is kind of a generic one, V equals lambda F. And not all wave equations obey this law, but most of them do. And if you were to study, oh my goodness. I mentioned the surface of the sun and the plasma and all the waves going through the plasma and the magnetic fields on the surface of the sun. Very, very tricky, but the calculus equations take up about 7 or 8 pages. They are ginormous. They're just awesome. I mean, it's like the Godzilla of physics to study the surface of the sun. But if you look at them closely, they have a strong resemblance to V equals lambda F. There's a whole lot of numbers that represent a wavelength and a whole lot of numbers that represent a frequency. All kinds of calculus formulas, but it's basically a frequency. All kind of calculus formula, but it's basically a wavelength. And you multiply them. So the wavelength is the spatial distance peak to peak, trough to trough, equal phase to next equal phase. All right? The period of the wave is simply the amount of time separating two successive peaks. So if you're out sitting on the dock by the bay and you're watching the tide roll away, and the waves are going out in a certain direction, and you just keep, 0.1 second, 0.2 seconds, and you just keep time on those waves, eventually you'll figure out, the waves are going by about every 1.3 seconds, or whatever it happens to be. That's your period. 1 over that is the frequency. So lambda F, wavelength times frequency. Frequency is the inverse of the period. So the things that you measure are period and wavelength. All right? And then the frequency, you don't measure the frequency, you measure the period. But the frequency, you just go 1 over whatever the period is, and that's your frequency. All right? So let's take a look at the light as a special kind of magnetic field. All right, electromagnetic field, that means the stuff that affects compasses and the stuff that affects electrons and protons. You know, the electrons are held in orbit around the nucleus. The nucleus has got a bunch of protons in there. And there's a bunch of electrons circling around there. And they're held in orbit by the electric field. And then compass needles, you know, they deflect to tell you the way to navigate to the north. Those are those respond to the magnetic field of the Earth. Now, the electromagnetic field forms a spectrum. And if you type in electromagnetic spectrum in Google or DuckDuckGo or any other search engine, you'll see zillions of photos and images like this. You know, sometimes you'll see them side to side like this one. Sometimes you'll see them vertical. You know, either way is good. And so the spectrum of electromagnetic radiation, electromagnetic waves, starts with radio waves. These are the largest wavelength. Radio, long wavelength. Big wavelength, small frequency. So make a note of that for radio. Now, a little bit tighter wavelength, still pretty big, but a little bit tighter than radio, is infrared. And then in parentheses, put also microwave. You know, some engineers consider microwave, they don't think of it as microwave, they think of it as infrared. Other people look at it, something that they might say is infrared, and, you know, somebody else, you know, it's like NASA versus Lockheed. You know, the guys at Lockheed might think the same wavelength is near infrared, and the guys at NASA might think, well, we call that a microwave. You know, so there's a little bit of slop in the terminology. Then a little bit tighter wavelength than that is visible, Roy G. Biv. All right, and that's diagrammed up here. It's just a teeny slice, very teeny slice of the electromagnetic, and that's what we see with our eyeballs. Now, so that's kind of your medium range wavelengths. And hey, you guys, the longest visible wavelength, about 700 nanometers. Let me write that, or let me repeat that for you. The reddest red that you can see, about 700 nanometers. The symbol for nanometer is little n, little m. It stands for a billionth of a meter. 1 nanometer is 10 to the minus 9 meters. All right? And 700 of those, that's considered the longest red that we can see. Now, somebody in here might be able to see 703 nanometers, and somebody else might only be able to see 699. You know, so there's probably a little bit, and they say that some animals can see deeper into the infrared than we can. You know, so they might be able to see, you know, 742 nanometers. All right? Now, so the red end, 700 nanometers. The violet end, the V end, the purpley end of visible light, 400 nanometers. Okay? So violet is the shorter wavelength, higher frequency, and of visible. And red is the long wavelength, smaller frequency, and of visible. Okay, so 700 nanometers red, 400 nanometers violet. And then green's kind of in the middle there somewhere, you know, 500 and something. Okay? And your eye, your eye doesn't measure nanometers, but you can distinguish colors pretty well. All right. Now, above that, even tighter wavelengths, below 400 nanometers, ultraviolet. All right. So when you get sunburn, you're getting something in the 300s or deeper or smaller. And then even smaller than that, even tighter wavelength, X-ray. And then gamma rays are really, really, really small. Now, X-rays have a small wavelength, so in this picture, X-rays are way down here, all right, on the left side of this diagram. That's the small, short wavelength end. The reason that X-rays penetrate your skin and stuff is that they have such a short wavelength. Now, they can't penetrate bone very well, so that's why your bones show up on X-ray photographs. They have a certain film emulsion that responds to X-rays. The X-rays that get through, expose the film. The X-rays that don't get through, they don't expose the film, so it looks white. Right? And that's how you get an X-ray photograph. All right. Now, this in this wave equation, we got wavelengths and frequencies, and we've got speed. Now, the symbol is c. In that famous equation of Einstein, E equals mc squared. The rest energy of an object with mass m. Oh my goodness. I wish I could teach you guys about relativity. I wish we had another 2 weeks. A little bit, and I could teach you all the cool stuff about relativity. We don't have quite enough time. But E equals mc squared, the rest energy, this is the energy that we get from nuclear reactions. Nuclear fusion and nuclear fission. The nuclear power plants that we have, like Port St. Lucie, wherever it is, and on nuclear submarines and stuff. That energy comes from E equals mc squared. So C is 3 times 10 to the 8 meters per second. And so every second, light goes 300 million meters. $300 million meters, 300,000 kilometers. So it takes about 500 light seconds to get from the sun to the earth. So we measure the distance scale in the solar system, from the sun out to Pluto, light seconds and light minutes, light years to the nearest stars, etc., etc. Now, we're going to do some calculations. This is the wave equation for light. And just to reinforce, wavelength is spatial. So it might be measured in meters or centimeters, kilometers, etc., nanometers. And the period is temporal, so you measure that somehow, and then the frequency is 1 over that. All right? And the frequency, the unit of frequency, the period t is seconds. That's the metric unit of time. So the metric unit of frequency is 1 over a second, or seconds to the minus 1. Go ahead and write that down. 1 over second. That's the unit of frequency. Seconds to the minus 1. That's another way to say the same thing, 1 over a second. And then the metric system nickname for that, like the metric system nickname for units of force is the Newton. For energy, the joule. And for frequency, the nickname is Hertz. Capital H, E-R-T-Z. Abbreviation, capital H-Z. Now, it's not named after the Hertz Rent-A-Car Company. It's named after a German scientist. I can't remember his first name. Professor von Hertz. And Professor Hertz is the first guy back about 120 years ago 140 years ago. I think it was 1888. He measured electromagnetic waves for the first time. They knew the theory of it for about 30 years before that, and then it took him a while. He was the first guy to actually measure electromagnetic waves. You know, I should look it up how he did that. I should know that. I don't. I'll try to do that this weekend. And anyway, so he measured it, a certain frequency and everything. So now we call seconds to the minus 1, that's a hertz. Okay? And so what we're going to do now together is calculate a frequency for something for which I give you the wavelength. Red, 656 nanometers. Okay, that's a good red. It's not quite 700, so it's not the deepest red, but it's in there. It's red. If you were to look at a source of light at this wavelength, and we could do that in the lab. We use hydrogen for that. Yeah, it's red, definitely. Now, I give you an admonition. We're going to start doing some serious scientific notation, and even though you can use your iPhone, and I don't know about your Android phone, but I know your iPhone does scientific notation pretty nice, but you can't use your phones on exams. And I'm not going to tell you what's on exams, but you're going to want to know how to do scientific notation on the exam. Now, I'm going to show you how to do it on pencil and paper. If you have a calculator, you can do things even more easily. All right, so here we go, 656 nanometers. Now, we're going to take that wave equation, and we want to figure out a frequency. So let's park the wavelength lambda, which we know, 656 nanometers. That's going to go in the denominator, and the speed of light, 3 times 10 to the 8 meters per second, that's upstairs. And then we're just going to calculate it. And that's going to give me some number of hertz, some number of seconds to the minus 1, some number of per seconds. And it's going to be a big number for 656 nanometers. Now, if I give you a frequency and ask you to figure out a wavelength, hey, you guys, look at this one. This is the other version that you can use. If you know the frequency and want the wavelength, you just do the. Nice. That takes talent. It's all right. So this is boring. So you just liven things up nicely. So anyways, this is the other variation. So you're going to use either this one or C over lambda equals F. And that's what we're using now. We're using C over lambda equals F. So here it is. Here we go. 656 nanometers, lambda, in the denominator. And nanometers, I change it to 10 to the minus 9 meters. Because speed of light is in meters per second. It's not in nanometers per second. It's in meters per second. 3 times 10 to the 8. I mean, you could write it in nanometers per second. I've never seen anybody do that, but you could do it if you want. But anyway, so here we go. And on top, 3 times 10 to the 8 meters per second. So that's C. And then in the denominator, 656 times 10 to the minus 9. That's the frequency. And that quotient is going to give you the frequency. Would you guys like to dismiss a little early today? Maybe? Yeah, okay. Well, we're looking good. We're looking good. It might be a few minutes early. Now, there's C over lambda equals F. Now, for those of you that don't know how to use scientific notation on your calculator, you're going to have to follow my lead here. If you know how to do if you're asleep, Sawyer, yeah. He's still asleep. Leave him. Okay, hey, great. Good, all right. So if you're on your calculator and you know what you're doing, good. It takes 2 seconds. If you're not, here's what you want to do. I always take that, if I'm doing this on pencil and paper, I take that 10 to the minus 9 in the denominator, and I change it into 10 to the regular 9 in the numerator. All right? Division by a negative exponent is equal to multiplication in the numerator by the regular exponent. So 10 to the minus 9 downstairs is the same as 10 to the regular 9 upstairs. So upstairs I've got 10 to the 8, and I've also got 10 to the 9. And downstairs, I'm going to leave that 656 down there. So here's what I got. I got a fraction 3 over 656, and I got 10 to the 17, and I got per second. And notice that I didn't really mention it, but I'll mention it now. I also canceled meters top and bottom over here, okay? On the left, the first fraction, yeah, meters cancel. Per second doesn't cancel. That's my hertzes. But that's what we want. We want a frequency in hertz, so we don't want to get rid of that. All right, now, if you're on pencil and paper or a calculator and you're really rusty, here's what I would do. I would go like this. 3 EE17, and that gets me the stuff on top. I've got a 3 on top, and I've got a 10 to the 17 on top. And then divide by 656. Now, on a calculator, it's going to give me something point something, and then a little tiny number depending on the kind of calculator you have, upstairs. Now, who's got an answer? Raise your hand if you've got an answer. What do you got in the red? 4.57 times 10 to the 4. So 4.57 times 10 to the 14. Anybody verify that? And it's going to be like, depending on the calculator you have, what kind of calculator are you using? Your cell phone? Oh, it's a little TI? Yeah. All right, if you're using your cell phone, it might look, I think it'll be like a E and then a minus, an E and a 14 or something. So you'll have to get used to that if you're using your calculator. But at any rate, here's what you got. So there's your answer. Now, the problem with that is I don't ever ask you for scientific notation answers. It's too tricky. So what I'm going to ask you is, how many terahertz? Now, a terahertz is 10 to the 12 hertz. Now, I've got 10 to the 14 over here, so I've got 100 terahertzes. So this answer, 4.57 times 10 to the 14 hertz, Mark, is the same as 457 terahertz. And that's what I'm going to ask you to type in, 457. I mean, if this were the question, that's what you would type in. I don't want you to type in a power of 10. I don't want you to type in terahertz. All right, now here's why I say you can type that in as 457 terahertz. This 10 to the 14 over here, that's the same as 10 to the 2 times 10 to the 12. All right, 10 to the 12 is the metric or tera, capital T, that's this capital T over here, that's the metric system abbreviation for powers 10 to the 12. But you also have, now you separate 10 to the 12 out, and you still have 10 to the tooth. All right, so you just put that in with the 457. So 4.57 times 10 to the tooth is 457 even. Ding. And then here's your terahertz, 10 to the 12th. So if you're writing it out, if you know, I'll tell you what, if you guys were engineering majors and I was giving you a written exam where you write out your everything and you calculate it, if I saw this up here, ding, you got it. But since we're going to be doing clicking, this is what I want, 457. All right, now we're going to do an example of that in just a second. Get your clicker out. We got another question here. But this first one, this is going to give you a meltdown, a small meltdown, a visual IQ test. Question first. 10 to the 14 came from this calculation. All right? So the answer there is for, and do you have a cell phone with scientific, see if you can, this next calculation that we're going to do, see if you can do it scientific notation, all right? And, give it a shot, but you're definitely going to want to get used to doing this. Okay, question number 3 for today. Visual IQ test. How many wavelengths have we got? How many waves are there between A and B? How many full squiggles? I see people going like this. Good. Oh dear. Where did she go? Where did Sedora go? She took her bag. Okay, you guys ready? Okay, 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hurry up. Okay. 34% of you voted for C. Let's just see. So is that true? Two full wavelengths? All right, so there's a wavelength, right? So this red arrow, peak to peak, that's a wavelength, right? Now, let's start at A. So mentally, you got to start at A. All right, so there's one wavelength. All right, now let's shift it. The right end will shift to the right, and the left end will shift to where the right end is now. Zing. There's 2. And then, bonus time, another lambda over 2 right here. So the answer is 2.5. And 50% of you got it right. Now, all right, so that's a little IQ test. You might see questions like that on the next exam. All right, hit the refresh key. Let's do a numerical calculation. Lambda equals 410 nanometers, kind of like the one we just did. Okay, hit refresh. Type in your number and then hit the send key. Now this is violet. The one we did before was red. 656 nanometers. This is down at the bottom of the violets, 410, almost into ultraviolet. Yeah, Rosie. If it's nanometers, yeah, and I'm mostly going to ask you stuff about nano. But if I ask you to calculate a wavelength, that's going to be, like sometimes I give you an FM wavelength. That's going to be 10 to the 6 hertz. And then when that goes in the bottom, it's going to be it's actually a little easier. FM and AM. AMs are like 10 to the 3 hertz. FM is 10 to the 6 hertz. Cell phones are 10 to the 9 hertz, gigahertz. So if I ask you to calculate a lambda, it'll be a little easier. The frequencies are kind of, And so double check with your neighbor. Definitely make use of your brains. if you still have any left. If you haven't sneezed all your brains out. Hey, Harvard. Yo, Harvard. That was good timing. Right when I wasn't talking, nobody was talking, and so. But you know what? I think it's on the YouTube. Excellent. Hall of Fame. Round off carefully. You're round off carefully, round off normally, and you're going to get something in the hundreds of terahertzes. You know, visible light is hundreds of terahertzes. So if you have a whole number of terahertz between 0 and 10, you forgot your powers of 10. You guys got it? You got your answers? Did you guys get your answers in? Yeah, okay. How about you guys? Okay. Daniel. Did you get your answer in? Yeah, your calculation. Did you get it in? Did you click it in? Okay. Yeah. Good. Okay. Bailey. Where's Bailey? She's in this section? No, I guess not. "30 seconds. "20 seconds. "10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Raise your hand if you're doing that deliberately. Raise your hand if you answered 732. Sweet, that's the correct answer. All right, now, are you guys ready to dismiss? Okay, homework 19 and 18 this weekend. I'll see you next Tuesday.